So Michael is a chemist, and I'm a little unsure myself as to exactly what kind of chemist he would describe himself, whether it would be an organic chemist or an environmental chemist or exactly what. But if you look at the range of different kinds of things he's worked on, whatever the description is, it would be a very broad one, looking at a very wide range of, I guess, environmental chemical applications in many practical and other senses. Michael was trained at the University of Cologne in Germany. He subsequently worked in Japan and a number of other locations in the Asia Pacific region. He came to JCU in 2009, and we're really looking forward to hearing Michael talk today about chemistry in the tropics, sunshine, biomass, and water. Michael.
Thank you very much. So maybe to start with, it's actually Michael Oelgemoeller, but something is good enough. I'm an organic chemist by definition, but as the title suggests, and already Bill mentioned, I'm actually pretty much everywhere. So thank you for joining this presentation. I'm sorry I couldn't come to Cairns. I had babysitter duties today, unplanned, but hopefully the connection will be stable enough so we can enjoy a little bit of chemistry together. I'm aware that there are not only chemists here today, online and present, so I will try to keep as much chemistry as possible out and rather give an introduction on some research projects that hopefully fall within the flavor of TESS and some of the other people in the audience. So in short, if you look around you, maybe not today in Townsville, but usually we enjoy a lot of sunshine. We have plenty of biomass. We don't have so much water, so probably water is one of our precious resources that is worthwhile then also protecting. I want to start, however, with reminding some of you of the importance of chemistry. First of all, globally, chemistry is a very broad area. It covers everything from the popular things like pharmaceuticals to the less popular things like pesticides, but also plastics, etc. So in other words, it's everywhere. It's also a very big business. So globally, it's worth approximately $4.1 trillion. It's a big chunk, but even for Australia, chemistry, as you believe it or not, is the third largest manufacturing business and contributes about 35 billion Australian dollars to the GDP. Employs approximately 60,000 people directly, and an additional 200,000 jobs are linked to the chemical industry in Australia. Well, unfortunately for us, a lot of that is further in the south, but as I hopefully will show you, there are some smaller activities also around us. If you look at the public image of chemistry, however, very often chemists don't enjoy the best publicity. So usually when you say I'm a chemist, you almost have to apologize for that. It's of course linked to things like pollution, poisons, waste, also chemical weapons, etc., etc. But while chemistry may be responsible for this and contribute to this, it also has the solutions for some of these areas. And hopefully I can show you that what we are doing contributes to some of that. So if you look at my core research activities, I'm actually a light chemist, which means I use light to drive chemical reactions. And if you look at the 4 areas that I'm highlighting here, that starts with light-induced synthesis of biologically active compounds typically, but it also then goes to solar chemical production of chemicals using mirror systems. And you will hopefully rightfully already say that Queensland is a perfect location for that. But we are also dealing then with new technologies for photochemical synthesis. So we have pioneered the area of light on a chip. And we're also looking at scale-up of photochemical technologies. And finally, we are dealing with light as a way of degrading pollutants. So in particular, pharmaceutical residues that are widespread now in the environment. But we also investigate the stability of cosmetics and polymers. And this is outside our old chemistry building. It doesn't exist anymore. This sign was about 2 years old. It faced the sunny side on campus, and what you see then is photodegradation, not thermal degradation, of the polymer basically that covered this sign. So overall, I fit very well into JCU because JCU's motto is Crescente Luce, which translates into light ever increasing. However, I'm not really fully embraced. And I've also decided to actually focus here today on two non-photochemical projects because I think they are more relevant to TESS and the activities. And the first one is our project on the development of sustainable insect repellents. And I want to always tackle these in a typical JCU way. So there is a challenge or a research question. Then there is a solution to that, hopefully, or an approach towards a solution. Then, of course, we can see the results. So when you look at common mosquito repellents that are out there, DEET and picaridine are probably the most common one that you've all probably used already. They are not very pleasant. Some of them have significant health risks. DEET is actually classified as a solvent. It damages textiles and other things, so they are not very pleasant things. They are also made from petrochemicals, so they're not coming from a sustainable source. So the approach that we've been following is Mother Nature offers a lot of chemicals, in particular through essential oils. And we have identified or re-identified PMD as a natural or naturally derived insect repellent that is readily available here in Queensland because it comes from a common tree that grows here, which is lemon-scented gum. And you can see a picture of this tree already here. So what we've been doing over the last 4 years in particular is we have looked for the best source of this particular essential oil. We then looked at the conversion of one of the main ingredients of this oil towards this natural repellents. And we then also helped commercializing it initially in New Caledonia, but also now in far north Queensland, namely in the Kuranda region, where we're currently redeveloping this process or repeating the success of the project in New Caledonia. And you can sometimes see us also sampling. So we do sample occasionally ourselves. We do extractions ourselves. We have the facilities in Townsville. And we also have then the reactors to do 10 kilogram conversions of these essential oils. And of course, finally, we then also do the quality control, or we did the quality control for some of the commercialized formulations that are then sold, for example, in New Caledonia. It's a very exciting project. It's a very nicely smelling project. And as I mentioned as well, it has led to the commercialization of this product in New Caledonia, where insect-borne diseases are widespread, in particular dengue. Now, a little bit more on this PMD repellent. You can see the structure here on the right side. It's a very basic molecule. Goes by this abbreviation. The full name is also written out here. It's like Oelgemoeller somewhat. And it is a proven repellent. So it's a very effective repellent against a variety of mosquitoes, including also the one responsible for diseases like dengue. It's the only natural repellent also recommended for malaria control. And it has proven efficiencies not only against mosquitoes, but in a variety of other biting insects like midgets, ticks, and stable flies as well. Like most essential oils, it smells beautifully. It has a very pleasant cooling effect, and it also has a very low risk to human health. The LC50 is above 2,000 milligrams per kilograms in rats. So you need to swallow a lot of this in order to get some harmful side effects. And it's already out there, so it's been approved. It's not something new. It's not something we invented either. So the repellent is already out there. It's synthetically synthesized from artificial precursors, but it's also synthesized from the essential oil as well through a refinement process. So PMD is either obtained in a pure form and then mixed with certain ingredients to make a formulation, or you take lemon-scented gum oil, you do a very simple, basic kitchen chemistry conversion of it, and you enrich then the PMD content in the essential oil to quite high levels. These materials then go under different names. For example, the recommended name at the moment is oil of lemon eucalyptus, hydrated cyclized. That describes very well actually where this compound is coming from chemically. However, it's a pretty cumbersome name, but it's also known as PMD rich botanical oil, PMD RBO. And because this is the name used on or in New Caledonia, I will refer to this refined oil from now on as PMD RBO as well. It's, as I mentioned, a semi-synthetic refined version of lemon-scented gum oil. However, the Chinese have been using it or have known it for a very long time under this name down here. And they obtain it either from the waste distillate or from the water-soluble fraction after the steam distillation of lemon-scented gum itself. So it comes from a different source there. The PMD content of these refined oils is typically above 60%, at least that is desirable. And if you look at a commercial formulation that contains this refined oil, we are talking about 20 to 40% of the active repellent. You need at least 20 to 40 or 20 to 25% in order to get a good efficiency. And again, the oil or the refined oil has been tested and has been shown to protect for up to 6 hours. And it often even exceeds the activity or efficiency of the common compounds, for example, DEET. It's a very, very nice molecule, by the way. Very nice smell. Anyway, I mentioned it already. It comes from a local tree. So here, it's a Queensland-owned tree, not necessarily an Australian one. So lemon-scented gum, also known as Eucalyptus citriodora, although it has been reclassified, now called a Corymbia citriodora tree, grows pretty much all over Queensland. I'm pretty sure you will find one within 1 kilometer where you are at the moment. There are very small populations also here on the JCU campus in Townsville, where we did sample and extract then oils from. So it's a local tree. It grows in Queensland naturally, but there are also some wild populations in New Caledonia. If you're familiar with New Caledonia, it's like a long sausage-shaped island, more or less. And at the top, in the far north, you have some small populations of these trees. They are not native, they are invasive. Nobody knows how they got there, but they are actually used already for essential oil extraction. And the essential oils have been sold already in New Caledonia as well. What we do is we do wild harvesting then with our industrial partners as well. So we don't plant this tree, we go into the bush and we chop a couple of branches off. So we're not gonna cut down the entire tree. And it's a very sustainable way, obviously, of harvesting this. And there are 2 distilleries in New Caledonia, one in Boulou-Paris, which is not far from the airport in New Caledonia, the other one far in the north, and they're both producing this oil as well. Here in Australia, it's also farmed. It's also harvested wild up in Cairns, or there's a plantation even in New South Wales where you can buy then larger quantities of the oil. Anyway, if you do the analysis of a typical oil of lemon-scented gum, this is the chemical composition. Maybe first worthwhile mention is it has a very poor repellent activity. So it protects you only for about 22 minutes on a 20% formulation, which means you need to constantly reapply it. It's too volatile. And if you do the chemical analysis, these are the main ingredients of which PMD, the actual repellent, only exists in trace amounts to, or if you're lucky, up to 5% of the total. However, PMD is a product of citronellal. So citronellal is the main component of this oil. And what you can do now is with simple kitchen chemistry, you can convert citronellal into PMD, and you can enrich then the PMD content of this oil, and you get then what we call PMD RBO. So a couple of years ago with the university in New Caledonia, we launched a project, and the aims of this project were to, first of all, get our hands on as many of these essential oils from all over the world, if possible, to then check the chemical composition to identify the oil that is the best suited as a precursor for the PMD production. And of course, then to develop a process in the lab for the conversion, and then to also ensure compliance with the regulations in New Caledonia, that is TESS New Caledonia. It's comparable to Queensland Health. So they state that in order to be registered and to be used, any formulation containing PMD must contain between 19 and 25% of the active repellent. Not below, above that is unnecessary, but a lot of formulations actually do not reach these percentages, so they are not very efficient as a result. Anyways, what we did then is we gathered lemon-scented gum oil. We also collected some at JCU, but it wasn't that great, so it's not in this table. And we did a basic comparison. We did a GCMS analysis with our colleagues in New Caledonia. And we were looking for the oil that has the highest precursor content, so the highest amount of citronellal. And we were delighted to see that the far North Queensland oil actually was initially by far the best oil. The original oil we sampled in New Caledonia, in contrast, was the worst one, which was only 47% of the precursor, which suggests that it was more or less a hybrid and not a purebred lemon-scented gum anymore. However, our collaborators in New Caledonia went back into the bush and they have identified a new population. And when we did the analysis of this new species, we actually confirmed that they had found a similarly good population or tree or species in New Caledonia, which was quite exciting. You can see that there are other Australian oils in here. So New South Wales, Western Australia, we beat them by far, by a few percent always. We also got our hands on an oil from Madagascar, Brazil, and China. And as you can see, while they have citronellal as the main component, is not as good as the one from far North Queensland. Anyways, just to show you now what a typical analysis looks like, here you can see the GC chromatogram of the Brazilian lemon-scented gum oil, which we obtained in 2020. It's a typical GC profile here. I've only highlighted some of the peaks. And as you can see, citronellal is the peak at approximately 18.3 minutes. It really is the dominant peak, and it converts to about 70%. We do then the assignment with the help of standard compounds or with literature retention indices. Our colleagues in New Caledonia are more lucky. They have a GCMS that allows them to assign peaks based on molecular mass. So they can do that a bit quicker than us, but nevertheless, for a simple oil like this, we can do this ourselves as well. The chemistry then is really kitchen chemistry now, and that's what I like about this process as well. So citronellal is treated then with acid, catalytic amount of acid in water at 50 degrees, and it cyclizes then. It also captures a water molecule and it forms PMD. Industrially, this can be done with battery acid or sulfuric acid, but we were very pleased to find an alternative procedure reported by Drapeau in 2011 that used citric acid. Citric acid is, again, a natural product, so it's a much greener and more sustainable process. And we have then also started to scale this process up up to 10 liters. You have an emulsion initially, so the oil doesn't dissolve in citric acid, in aqueous citric acid. The oil usually sits on top, so you have to generate a very nice emulsion. You then stir the whole thing for up to 16 hours. And on my lower right side, you can see a typical conversion over time profile then for one of the oils. It's a Brazilian oil again. So it started with approximately 74% of citronellal. That then went down. At the same time, the PMD amount went up, whereas all other compounds remained more or less stable. So they don't care about citric acid and water in 50 degrees, which is good because you don't have to worry about them being degraded or whatsoever. The only thing that you see as well is isopolygol is a small byproduct of this process. So if you look at the amount of isopolygol, which is a blue line, it slightly goes up. So it is formed, during this process as well, but very, very slowly and in a very controlled way. So out of the 74% that you have initially, you can convert about 65, 67% then into PMD. And if you look at the batch data here, so we have produced, with the help of this reactor here, up to 4 kilograms of PMD RBO within a day. Just to show you the chromatogram as well. So it's the same compound that you saw earlier. The citronellal has completely disappeared. Isopolygol is still there. Citronellol is still there. And here now you have the peaks for cis and trans PMD. So PMD is not a single compound. It's actually a mixture of up to 4, of which 2 are dominant. They're called then cis and trans. And you can see them clearly here around 28 to 29 minutes. And if you do the integration, of course, of all the peaks again, you can then determine what the amount of PMD is. So we did this, we developed all this, the procedures, and then we went back to the distillery de Blue Paris, our partner in New Caledonia. They have been manufacturing this and selling this already since February 2018. Either online or in their little boutique shop in their distillery, but also on local markets. And it has been a bestseller. So they were extremely happy with this compound. Consumers were very happy with this compound. So they couldn't really meet the demand anymore. Then the owners changed 2 years ago. So the new owners then this year decided to purchase a professional reactor to do this conversion themselves. And we assisted them as well here in the purchasing of this equipment. And they are also currently looking for the registration of their products so they can actually export them. Unfortunately, they have just experienced quite a drawback. They had plans to plant lemon-scented gum in New Caledonia, but because it's considered an invasive species, this was denied. So they are still depending on those few wild populations in the far north, and that will limit their production, of course, significantly. Nevertheless, in 2020, we produced about 25 kilograms of PMD RBO for them here at JCU, and we delivered it to them, and they converted that into, I don't know, several hundred batches of their product, and they are selling it in these flacons here as a roll-on. They want it 100% natural. So what they do is they take between 20 and 30% of the PMD RBO, the refined oil, and then they mix it with sunflower oil. It's a little bit oily, but nevertheless, it's 100% natural. And of course, we also advise them on the dilution in order to meet the required active repellent potency. So very, very exciting for us. We stepped aside now a little bit, and they are now taking over themselves. But we are actually, for the last couple of years as well, repeating this. success, hopefully, with the rare earth oils distillery up in Kurunda in far north Queensland. So there's a small distillery there as well. They also have a shop in Kurunda, very beautiful product portfolio. And so far we have produced for them also about 15 kilograms of this refined oil. However, they are a bit more professional, so they are aiming at registration first and then selling it. And they are also more interested in water-based formulations, not sunflower oil formulations. And they are quite experienced also with formulations themselves. And I'm holding here into the camera the first two prototypes of a lotion containing this repellent. Smells really, really nicely. It's like a whitish solution or cream. And at the same time, a water-based spray formulation, same thing. So very, very nice products already, and not as oily as the ones from New Caledonia. So hopefully you will see it in Cairns probably first, but then also later all over Queensland on the shelves. That was my first project. Just want to check how am I doing, very, very slow. And I want to now talk about a project that I've done with Lynn Schwarzkopf. Lynn Schwarzkopf was the leader as well of this project. And I helped her developing a cane toad control agent. The whole thing was supported by ACTA, which is a company that does animal control technologies, has been working with Lynn for a very long time, as I understand it. And together they had developed this very successful cane toad trap already. And I think it's called Toadinator or something like that. But what do you do then with all the toads when you have collected them? Well, you need to get rid of them. So you need to euthanize them. And if you look at the recommended methods at the moment, there's not much out there. The recommended method, according to Sharp et al. Here, is that you stun them here on the head, and then you decapitate them with a spade or so. You can do that with a single toad, but not with 2 dozens that you have in your cage. CO2 gassing for 4 hours at least is also not very efficient. So obviously these recommended methods are not very practicable. And then there are the others, the probably methods that most of us utilize. They are considered cruel or inhumane now, and some of you may be surprised that freezing cane toads is no longer considered acceptable. And neither is the treatment, of course, with Dettol or Victa. If you don't know what Victa is, it's an Australian lawnmower. And if you have some time later, just go into YouTube and search for cane toad and Victa, and you will see a actually quite remarkable cartoon on cane toads meeting this particular machine. So the idea then of Akhtar and Lynn was, okay, we need to find something else in order to kill cane toads also humanely, as much as that is possible. And the idea was, well, why don't we use any anesthetics that's already used for amphibians or other control agents that are out there, and just oversupply, so overdose these. So, and okay, let's do that then. There was a product, or there is a product already on the market. It is called Hopstop. It's conditionally acceptable according to Sharp. It was commercially available at Bunnings for a while, but they have withdrawn it. You can still buy it online. So Hopstop is nothing else but another version of Dettol. It's not exactly Dettol, but it contains the same active ingredient, which is this chlorophenol down here in about 3 to 6%. However, when you read the feedback on this product at Bunnings, it's quite mixed. Some people are very happy with it, but others aren't. And the first one I want to show you is somebody saying, well, it didn't really kill them. So they were knocked out, but then they hopped away eventually. And another person complained that it was quite expensive. So while it was effective, he ran out of money and the cane toads kept on coming. So obviously there was an interesting project here. There was nothing really on the market that was 100% satisfactory and was also then considered humane. So ACTA guided this project. So they also told us what active ingredient they wanted us to study. And out of the ones, you can see them all here. So it started with phenoxyethanol, eugenol, and clove oil, isoeugenol, benzocaine, either free or in the salt form, tricane mesylate sodium nitrate, which is used for feral pigs, by the way, and then sodium monosine as well. So we screened all these. We unfortunately became aware that as we were working on this, a new product had entered the market. It was initially called Toad Blitz, but it's actually sold now under the name Croaked. And it contains 112 grams per liter of eugenol. However, that was already known that eugenol kills cane toads. So there was no novelty here. There was no potential for IP protection using eugenol. But nevertheless, because this product became available, we used it as a reference. We did then screening also in 3 different carriers. So water, then ethanol, isopropanol, and propylene glycol. And very quickly, 2 compounds or a combination of 2 of these became then our focal point. That was phenoxyethanol as the active ingredient and isopropanol as a carrier. Isopropanol is a makeup remover, so I'm pretty sure a lot of you have it at home and use it to remove makeup in the evening before going to bed or before calming down and enjoying the afternoon. I've given you also some of the structures here just to show you that I'm the chemist here. Benzocaine was also quite good in the trials themselves, but it degraded very quickly. So it wasn't stable enough. So it was eventually excluded as well. The screening was done in brief as follows. If you're more interested in this, you can look at our patent here that I just found a couple of weeks ago. I was very excited, obviously. So usually 6 adult toads were chosen for the trial, plus 1 as a control that was only sprayed with a carrier. Then about 1.5 milliliters of the formulation was sprayed, most of the time on the back of the toad, but sometimes also on the other side, so the belly side of the toad. For practical reasons, I'm pretty sure most of us just don't want to pick up a toad. They want to spray it from behind. So obviously the spraying on the back is a preferred method here. And toads were collected and the solutions were made just the day before or 2 days before. The toads were calmed down initially and then they were sprayed. And then they were monitored for up to 24 hours for their behavior, like when you turn them around, are they trying to get back onto their bellies? Are they showing any vital signs like breathing or heart rate? And are there any side effects visible, like erratic movements, discomfort, bloating, color changes, whatsoever? And after typically 48 hours, they were then euthanized and they were dissected then in order to check, is there really normal heart rate, yes or no? And of course, in a perfect world, what we wanted is that the 6 toads that were sprayed were all dead and rest in pieces, whereas the 1 control toad lived happily ever after, meaning until the next trial, when it was then its turn as well. So as I mentioned already, phenoxyethanol then quickly became the compound of choice. And here you have a table now that shows you as well certain concentrations, certain carriers, also in combination with eugenol, and what the mortality rate was for how many toads, and what was the approximate time until the toads were non-responsive. That's the first time indicated here. And then when they were no more, when they were not showing any vital signs anymore, which is in the second time number here. And as you can see, at a concentration of 140 grams per liters, we reached for a quite large batch of 22 toads, 100% mortality, and it took about 20-ish minutes for them to die really, really calmly, whatever that means. When you go down with the concentration, you may have a survivor, or it may take longer to reach mortality. So I think 140 grams per mole is probably the concentration I would recommend for the final formulation. And it's also in a similar range than this toad blitz or the croaked compound, which is the lower one here. So we made our own version of it. So you see eugenol and isopropanol with 112 grams per liter, just like croaked itself. For 6 toad caused 100% mortality. And it took a total of 20 minutes as well. So phenoxyethanol, a very, very basic, very cheap chemical, is actually very, very efficient in order to control toads. Eugenol is a very colorful compound, also smells very strongly. So phenoxyethanol doesn't have this problem. It's a colorless liquid, doesn't have a strong eigen smell either. So it is, from this practical perspective, actually more advantageous than eugenol itself. The only issue is it does attack plastics. So the plastic parts of the cane toad trap, they need to be protected. You shouldn't be spraying on it. But overall, it was a very exciting project. And I thank Lynn really a lot for inviting me here. And also ACTA, of course, for allowing me to join this project. And you see here how chemistry can contribute. The last thing I want to say is eugenol also showed some side effects, like some of the toads that had pink bellies. However, it was believed that it didn't bother them anymore. They were dead anyways. So there were no signs that it caused any discomfort before they passed away. Now, finally, in my last maybe 20 minutes or so, let's finally talk a little bit about light-induced chemistry and maybe more tropical chemistry as well. And the first one is also closest to my heart, and one of the reasons why I came to Australia and to Townsville in particular is the solar manufacturing of commodity chemicals. So what does that mean? There are very few light-induced industrial processes out there, in particular for the fragrance industry, so for certain high-value chemicals. And if you look at the published data for these processes, they require very strong UV lamps that are operated then for several days in order to generate 10 to 70 kilograms of a fragrant in this case. Depending on the energy costs, you can already think about how much does that cost just to run the lamps in doing this process. When you think of more traditional heated chemical transformations, you can ask the same question. Heating is expensive as well. You have to put electrical energy into this. However, there are a lot of photochemical processes that can be done outdoors using sunlight. And as such, you can do very efficiently solar chemistry. And the products that we have targeted in this research here are starting materials that we again get for relatively low prices from our local biomass, be it sugarcane bagasse, be it essential oil components, and we then convert them with the help of sunlight into these target molecules here. And there are fragrances among them, there are herbicidal compounds among them, there are anti-malarial compounds among them. And all these compounds are synthesized through a so-called photo-oxygenation reaction, where oxygen is used as a reagent gas. In order to use that, you need to activate it with the help of a dye, and dyes are colored because they absorb visible light. So here we have a photocatalyst in these reactions that uses natural visible light. And as such, these reactions can be done outdoors. And also important, these chemicals here are only needed in up to, let's say, 100 tons a year. And that is a doable production scale, of course, keeping in mind that solar chemistry can only happen during the day. and also when you have sunny conditions and not necessarily during the rainy season. But 100 tons you can produce in a couple of weeks. You don't have to operate 24/7, 365 days a year. So very interesting chemicals here, also with applications for the tropics, like fragrances, of course, and agrochemicals and anti-malaria agents, not for us necessarily, but at least for our northern neighbors in PNG, where malaria is so very, very common. Just to start, you don't have to be in Townsville in order to do this chemistry. Bill didn't mention that I actually came from Ireland, not from Germany or Japan. And I did very successfully as a young lecturer, solar chemistry under Irish sunlight. And the way we did it, we basically took a flask outside and we exposed it to Irish sunlight. Now, Ireland or Dublin receives around 1,400 hours of direct sunlight every year, but you get it in 10-minute fractions. So you don't get, larger periods. Nevertheless, it was good enough to demonstrate that you can use Irish sunlight to drive this reaction here towards completely new target molecules. These are quinones. They were previously unknown, and we synthesized them on a small scale in a flask with yields up to 90% within 6 hours of solar exposure. We also did the same reactions indoors, and as you can see, after 4 or 24 hours of irradiation now with a halogen spotlight that you have maybe in the garden, you get lower or comparable yields. So Irish sunlight is good enough. You don't necessarily need UV indices or 12 or whatever. Nevertheless, at the end of the day, it's a question of economics. So solar chemistry in Ireland may work, but it's not economical. And here we are now in beautiful and sunny Townsville, not today though. And of course, once I came here in 2009, I launched what I call solar chemicals from and for the tropics. As mentioned earlier, we have all these natural compounds around us from agricultural waste or from essential oils, and they can be converted into something much more valuable, like a fragrance. So the value of this product is suddenly 10 to 100 times more than the original compound. And if you start with waste, it's even higher than that. So we started to turn bio-waste chemicals from local biomass more or less into these expensive products. And as you can see here, we have a variety of reactors to do that. We can do this on scales up to 100 liters using this reactor that you see here in the back. That is a reactor similar to your hot water system you may have on your roof. However, it contains glass tubes that are here in parallel, and you push or you pass your solution then through this. It's a very colorful chemistry, very beautiful. However, most of the time we are working on smaller scales. The reason is we are not chemical engineers. So 10 liters is something we can do. 100 liters, we do that every couple of years. You need a lot of reagents for that. Nevertheless, we demonstrated some years ago, or maybe just to give you now the numbers for Townsville. So Ireland was what, 1,300 or so hours of sunlight? Townsville gets 3,100 hours of direct sunshine. That's even a couple of hundred hours more than Cairns. I looked it up the other day. Cairns is significantly lower than that. So Townsville is the location to do this kind of research. And some years ago, we did this chemical conversion here. Don't want to bore you too much. You start again with an essential oil compound, citronellol and alcohol, and in 3 steps, you convert it then into rose oxide. As the name suggests, it's a compound you find in roses. It's a very, very valuable fragrant. It's basically in every fragrances these days in small amounts. The annual demand is somewhere about 100 tons a year for this compound. And it is quite easily isolated from this reaction. So it's a very interesting reaction. You do a lot of traditional old school separations like steam distillations, and you get then a very versatile and very valuable product out of this that you could theoretically sell. So some years ago, we produced about 2 kilograms of that using 5 liters of the starting material, 45 liters of ethanol, of which we could re-isolate about 80%. Took us 7 days. The problem was not the solar chemistry. The problem was we may have this reactor here that allows us to work on this scale initially, but we do not have the equipment to strip 45 liters of ethanol from the final product solution. So basically, we were constantly looking for so-called evaporators in order to concentrate our solutions, etc., etc. We could have done it in 2 days if we had the proper equipment. We also did some guesstimations on the costs. So we spent some money on getting all the reagents, of course, in, and then we looked at how much did it cost us. And at a very competitive price, we made rose oxide for about 63 Australian cents per gram. It costs a few hundred times that much if you buy it yourself. Just for comparison, rose oxide, although a natural compound, it only exists in traces in rose oil. And rose oil is obtained from about 3 tons of rose blossoms. You obtain then 1 liter of rose oil, of which then about 1% or so is rose oxide. So you cannot really grow it and harvest it naturally. You are required, if you want to synthesize or if you want larger amount of this fragrance, you have to do this semi-synthetic process here again. Semi-synthetic because you start with a natural product and you then convert it synthetically in 3 steps into something else. So a very nice process, works also very well, and is industrially also done already. Because I'm German and Germans like to Uber-engineer things, we also partnered with the German Aerospace Center in Cologne. Now, the Aerospace Center in Cologne does not only shoot satellites into outer space and trains astronauts, they also had at the time, and they still have, a solar research facility close to the Cologne airport. And up to recently, they operated this mirror system down here. It's a mirror system that focuses sunlight, German sunlight now, 32 times onto a receiver tube through which you pass your reaction mixture. And because you have the power of 32 suns now, you can accelerate the reaction. So you can do it faster. And we demonstrated that in 2 large-scale reactions that we did many, many, many years ago. But we used about 8 liters or 6 liters of the starting material, citronellol. We then either used all the 4 mirrors here, only one of the mirrors of this system. And we converted now this starting material within 1.5 to 3 hours completely then into the next compound. We even demonstrated with the other 2 steps that we can isolate and obtain rose oxide in an overall yield of 50 to 55%, which is better than the industrial process utilizing artificial light. Why is that? Artificial light contains a lot of UV light, and UV light is very energetic and can degrade things. And you want to avoid this. Solar light has a very low UV content. The mirrors here are actually not even reflecting that. They only reflect the visible light. So you have less destruction happening in your reaction solutions caused by UV light alone. And what you see here then is how the starting material disappears. The other black line here shows you the solar quality of the light, of the sunlight. And the spikes that you see here represent a cloud field that was passing by. Now, this is a great reactor when the sun is shining, but when the sun is not shining, this reactor will stop operating. So it is great, costs a lot of money as well, and it has to withstand a lot of wind as well, because it is nothing but a big giant sail. And when the wind blows very strongly, it's going to fall over. So sometimes high tech is actually not the solution. Low tech, like the reactor that we operate, is a much better one. And another reaction I want to show you is here the conversion of furfural, which is a sugarcane bagasse derived platform chemical, into a molecule known as hydroxyfuranone. Hydroxyfuranone is a building block chemical, but it's also known as a herbicide. And it can be converted as well into certain fragrant molecules. So it's an interesting target as well for solar manufacturing. So a couple of years ago, again, we did a reactor comparison study using our big gun, using our medium gun, and using a small flask. And we then operated them in parallel on a sunny day. And as you can see, I just want to focus now on the big one here. So using 1.4 kilograms of the starting material and 30 liters of ethanol again, bioethanol again, we converted it to 90% into the product. Contains a little bit of a side product here that is formed under thermal conditions, but it's not really a big deal. And this then can be used for further reactions without any further purification as well. Just checking my watch here. How am I doing? So hopefully, if you don't mind, I just want to quickly go through the next area here, and then I can cut it short as well, which is water treatment. So light can be used to generate things, to make things, but as already hinted as well, it's also can be destructive. So it can degrade things. And if you look at typical organic or microbial compounds that you find in the environment, there's a lot out there. There are compounds known as the hazardous organic pollutants, HOPs. These are pesticides, these are pharmaceuticals, these are solvents, these are organotin, anti-fouling agents, etc., etc. They have all been found in the environment, and of concern these days are in particular pharmaceutical leftovers. Pharmaceuticals have a good reputation. However, they are biologically active, and as such, they can cause a lot of harm in the environment. And there have been now plenty of studies that showed that fish populations have declined, others have changed gender, vulture populations declined, fish are becoming more cocky because they actually drink antidepressant leftovers, etc., etc. So our precious reef is more or less under threat from all these organics, but also from certain microorganisms as well. And for us, Vibrio is an organism that is commonly detected in aquaculture. So we've been working on this as well. So our approach is use light, either directly, and I'm going to show you at least some examples for that, but also with a helping agent known as photocatalysis then is a very powerful way of degrading many, many organics, but also microbial pollutants. And of course, where do we see the targets here? We are not necessarily thinking here of cleaning up wastewater treatment plants unless they are small scales. In Ireland, we have actually collaborated with some pharmaceutical companies where we looked after their process wastewater that came out of the manufacturing of their pharmaceuticals. So it had a high load of intermediates of final products, whereas in the environment, you find very, very small amounts. Nevertheless, you can use light in combination with things. You can use, again, photodynamic therapy to kill some of these pollutants, and it works depending on what you're targeting actually very, very well. So in terms of the pharmaceuticals that we've chosen, there are three that became more or less our pets. They are very common pharmaceuticals. Diclofenac is the active ingredient of things like Voltaren. Amoxicillin is the most common antibiotic, and naproxen is just another non-steroidal anti-inflammatory drug. So these were chosen initially because they have been linked to environmental effects. They are frequently detected in the aquatic environment. They are potential environmental contaminants that can accumulate, and they are commonly prescribed or used if they are over-the-counter drugs. And if you read the literature, and here's just an example from a newsletter, it's very, very scary. Everything you can buy in a pharmacy has been detected in the environment and also in drinking water. Just to show you now, and I'm going to finish then after these slides here, maybe 2 more slides. So what we do is we start with the active ingredient. We then make a solution. The concentration usually far exceed the environmental concentrations that you find, but that has practical reasons. And remember, we were more or less also working with pharmaceutical companies where they had similar kind of like concentrations in their effluents. So light alone in a small laboratory reactor degrades diclofenac or naproxen within 15 minutes of irradiation very, very quickly, as you can see here. If you look at the HPLC chromatogram, your parent peak goes down very rapidly, whereas then other peaks are starting to emerge, eventually then disappear as well. And for diclofenac and for naproxen here, the structures of the main degradants are also shown here. We also work on other scales, but I'm going to skip that. Also in river water and in drinking water matrices, it works there as well. But just because the parent compound disappears doesn't mean that the water is now safe. You need to understand as well what is happening to these compounds as they get irradiated with light. So we have spent a lot of time as well trying to understand the degradation of these chemicals. And you can see a summary here for diclofenac itself. So it reacts very unselectively, which is not bad for degradation, in different directions, in different generations towards other compounds. The key now is you have to ensure that the other compounds are not more evil than the original one. And you also need to understand that light alone will eventually break it down to a smaller organic compound, but it will not mineralize anything to CO2, water, nitrate, phosphate, sulfate, whatsoever. So light alone is not good enough. You have to add a helping agent, but that is maybe for next time. I'm going to skip through the sunscreens here, unfortunately. So I just want to then finish here. So you've seen some of the things we do. I could talk for hours now here. So we do other things as well. And I give you a list here. At the moment, I would be very, very keen to find somebody to get back into the photodynamic therapy for aquacultural applications. We have done some proof of concept work with Kirsten Hyman there on algae bloom control and also on aquacultural feed sterilization, but I'm a chemist, so I need here a proper microbiologist in order to do that. Just to finish then here, this is my leaving slide. So I am one chemist at JCU. There are, however, more. There are a total of 6 research teams. And I really invite you, and I hopefully have shown to you as well, that we can help you with some of your projects. And we also have quite intensive facilities. So do not hesitate if you have a good idea or a crazy idea to get in touch, either myself or of course any of my colleagues. I apologize for running a little bit over. That is just the nature of the Zoom meetings. Usually you talk slowly. I thank you all for hanging in and listening. And I welcome now any questions if you have any. Thank you very much.